today's lecture we will start with the definition of a set. The question is that what is a set? Although it is easy to ask this question, it is not so easy to answer. What has been realized that this simple question leads to several more difficult questions. In this lecture, we are not going to discuss the difficulties which leads to eventually introduction of axiomatic set theory. Instead of that, we will discuss a somewhat working or operational understanding of a set. What we note that in mathematics or in several other applications, when we talk about things, we somehow understand a collection of things which we are interested in. For example, when we are talking about integers, that is 0, plus or minus 1, plus minus 2, plus minus 3 and all that, we rarely think of the set of elephants or set of cows or set of students. On the other hand, when we consider set of students, we usually do not consider the set of complex numbers at the same time, or we do not consider set of all possible subsets of the set of integers. Thus, there is an idea of universe which we will denote by script u. So, when we are talking about set of integers, then we will simply say that our universe u is the set of integers, the z which is the set of integers. We may be talking about real numbers, then u will be R, the set of real numbers, or we may be talking of the set of all students in IIT, the set of all students registered in the IITs. So, these are not numbers, these are human beings. Of course, we can label them by numbers, we can label them by names, but there is a trouble that names of two students may be same. So, possibly we will label them by their enrollment number and the name of the IIT and like that, but of course, they are not set of integers nor they are set of all subsets of integers. So, like that there are different scenarios where we have different universes. The elements of elements of a universe is called objects. That is the things that make up the universe. In case of integers, the objects will be integers. In case of real numbers, the objects will be real numbers. In case of the set of students, the objects will be individual students. Here we will use elements and objects synonymously. Now, once we fix a universe, then any collection of well defined objects inside that universe will be called a set, provided that the universe is not too large. We are not going to discuss the issues that when will the universe be too large and all the other complicated questions. We will simply take the examples that I have discussed already, and many such examples where this description of a set works nicely. So, we can even say that if we fix a universe fixing a universe any collection of any collection of well defined distinct objects is said to be a set. Now, of course, this is not a definition, it is just giving an idea of what we will mean by a set. It is not a definition because the question that what is a collection will be raised if we call this a definition, and then we have to define somehow the collection. The main idea over here is that we fix a universe. So, we fix the type of objects that we are dealing with, and within that type of objects we specify certain objects carefully, so that when we encounter an object in that universe, we are able to say whether the object that we have encountered has that specified property. And this collection or ensemble of these objects which within a universe which specifies properties is called a set. For example, if we consider the set of integers z, which is given by 0, plus 1, minus 1, plus 2, minus 2, and so on. If we consider the set of integers which are multiples of 2, that is set of even integers, we can easily determine, given an element in Z, whether it is even or not. So, let us call E as the collection of even integers. This collection E is a set. The reason is that we have fixed the universe, and once we have fixed the universe, if I say that I am interested in the set of even integers, then given an integer I can determine whether it is even or not, and then I can conceive of the collection of even integers. In case of objects which are not numbers, if I consider the set of all students registered in IITs, then we can consider the students registered in IIT Roorkee. So, the students registered in IIT Roorkee forms a set in the universe of all the students in registered in IITs. So, we have more or less understood what we mean by a set. Now, we move on to subsets. If C D are sets from a universe U, we say that C is a subset of D and write C or C if every element of C is an element of D. In addition, if D contains an element which is not in C, then C is called a proper subset of D, and this is denoted by C properly contained in D. Now, this symbolically will mean that for all sets C D from a universe U, if C is a subset of D, then for all x x in C implies x in D. We introduce some more symbols here, that is the symbol this and the symbol inverted A. This symbol, which looks like epsilon, means belongs to or belonging to or simply in. This means for all. Thus, the sentence that I have written here can be rewritten as for all x, x belonging to C. Here we have another symbol for implies, which is this one. So, I write over here, this means implies x belonging to D. We will be using these symbols very often. So, it is good to get used to these symbols. Now, there is another symbol that is used frequently, which is known as this. This means there exists. Thus, we will say that C is a proper subset of D, that is C a proper subset of D implies there exists x belonging to D such that x does not belong to the set C. The converse is also true, that is, if there exists x belonging to D such that X does not belong to C, and of course, here C must be a subset or equal of D, then C is said to be a proper subset of D. Now, we question that what is the idea of equality of sets, that is, when do we say that two sets are equal? For a given universe, U, the sets C and D taken from U are said to be equal and we write C equal to D if C is a subset of D and D is a subset of C. So, here we note the chain of arguments. First, we give an idea of a set and we give the idea of a universe, and then once we give the idea of a set, then we give the definition of the subset relation, that is, we take two sets from the universe and then we say that the set, the first set is a subset of the second set if all the elements of the first set are elements of the second set. So, that is subset equal, and if it so happens that the second set has some elements or at least one element which is not in the first set, then we will say that the first set is a proper subset of the second set. And then we say that if we have got two sets C and D, of course, consisting of the elements of the universe which we have fixed before starting all these discussions, then if it so happens that C is a subset of D and D is a subset of C, that is, all the elements of C are elements of D and all the elements of D are elements of C, then we say that the two sets are equal. This leads to some results related to subsets which are somewhat easy. Therefore, I will just write the results and leave the proof to the audience. So, the first theorem states that let A, B, C are subsets of U, that is, I have fixed U and A, B, C are sets. Then if A is a subset of B and B is a subset of C, then A is a subset of C. B, if A is a proper subset of B and B is a subset of C, then A is a proper subset of C. C, if A is a subset of B and B is a proper subset of C, then A is a proper subset of C. D, if A is a subset of B and B is a subset of C, then A is a subset of C. These are extremely straightforward results, and as I have said that I leave it for exercise. Now, let us look at some examples. Suppose we fix our U to something very small, that is 1, 2, 3, 4, 5. And consider two sets A 1, 2, 3 and B 3, 4. Now, we see that A, well, another set C 1, 2, 3, 4. So, we see that A is a subset of C, because A consists of 1, 2, 3 and C consists of 1, 2, 3, 4. Further, we see that 4 is in C, but 4 is not in A. Therefore, A is a proper subset of C. Similarly, we see that B is a proper subset of C, but if we consider A and B, A is 1, 2, 3 and B is 3, 4, then A is not a subset of B and B is not a subset of A. Next, we introduce another very special set, that is called the null set. So, the null set or the empty set is a unique set containing no element. As I have told before, that when we have fixed the universe, then a set in that universe contains some specific elements of the universe, or it may as well contain all the elements. The only thing that we expect, that when we say that A is a set in the universe U, then given an element or an object in U, I should be able to decide whether that object is inside A or not. Now, if A is whole of U, then the decision is easy, because if you give me any object, then I know by default that it is in A, because A contains all the objects of U. If A has some objects in U and some not and some objects in U are not in A, then also hypothetically we can have some kind of rule or listing by which we should be able to say that whether an object in U is in A or not. But this thing, when extended to the other extreme, where A does not have any object in U, then also A is a well defined collection of objects of U, because when we take any object in U, we know that it is not in A. So, A contains no object, and this is a very special set called the null set or the empty set, and it is denoted by phi or just two braces without anything inside. One result related to the empty set, which again is very obvious. For any universe U, let A is a subset of U, then phi, that is the empty set, is a subset of A, and if A is not equal to phi, then phi is a proper subset of A. So, this basically says that the empty set phi is a subset of any set A, and if A itself is not phi, then phi is a proper subset of A. The reason behind this is that we say that a set C is a subset of another set D, subset of D, if x belonging to C implies x belongs to D. Now, as long as this statement is true, that is any x belonging to C belongs to D, then C is a subset of D. Now, given any pair C and D, if we want to show that C is not a subset of D, then we have to find out an element x in C which is not in D, so that this statement is false. Now, the trouble here is that when C is equal to phi, then C has no element. Therefore, we cannot find an element for which x belongs to C and x not belonging to D holds. Therefore, we cannot prove that this is false, and therefore, we have to take that phi is a subset of D, or in the case of the theorem this is A. So, therefore, what we see is that the empty set phi is a subset of any set. We will do this theorem once more when we formally study logic in after some lectures. Now, we will briefly look at the problem of representing a set. So, one form of representation we have been doing so far rather intuitively is to put the braces around certain objects. For example, if we have certain names of students, like let us say Sudhir, Aman, Umesh, Dinesh, then the set containing these students possibly may be denoted by capital S and written within braces Sudhir, Aman, Umesh, Dinesh. Of course, we understand that these students are coming from some universe that we have fixed before. With numbers, we have already seen and we have been doing that. Suppose we want numbers from 1 to 5, that is integers from 1 to 5, we have just written something like this. Suppose I denote it by n and I write 1, 2, 3, 4, 5. So, in this way we can collect the objects and put braces around them and represent a set. But as is evident to all of us that if we have an infinite set or a very large set, it will be very difficult to write all the elements, or more often impossible to write all the elements within braces. Then we take some other other alternatives. For example, what we can do is that first we fix the universe U. Suppose I want all integers from 1 to 10,000, then fixing the universe U, I can write the set, let us say I, as x belonging to U such that 1 less than or equal to x less than or equal to 10,000. Thus, we can avoid listing down 10,000 integers by writing this inequality and understanding that U is a set of integers. But we have to be careful here, because it depends on how we choose the integer, how we choose the universe, because suppose we choose the universe to be set of real numbers, then instead of a set of integers, this same looking set will be an interval which I am writing as int between 1 to 10,000. Of course, it is possible to write other sets in the same way. For example, suppose we would like to write all the matrices, all the 2 by 2 matrices with real entries whose determinant values is non-zero. Then we may write it like this, that G is equal to A B C D such that A comma B comma C comma D belongs to R and A D minus B C is not equal to 0. Of course, this is an infinite set. So, I cannot write all the 2 by 2 matrices with real entries with non-zero determinant. I cannot list them, but with this notation I can specify them quite precisely. Next we move on to the idea of the power set of a set. Now, suppose A is a set of objects from a universe U, the power set of A is the set of all subsets of A. Now, let us look at an example. Suppose A is a finite set containing only 3 elements. Now, we start writing the set of all subsets of A. The first and the most obvious subset, which is a subset of any set, is phi, that is a set containing no element. And then we have the sets containing just one element, that is 1, 2, 3, and then we have the sets containing 2 elements, 1, 2, 1, 3 and 2, 3, and finally we have the set containing 3 elements, that is 1, 2, 3. And if we put braces around all these sets, then we have the power set of A, which we denote by P A. Now, if we count the number of elements in P A, we see that this is 1, 2, 3, 4, 5, 6, 7 and 8. We write that as simply writing P A within 2 horizontal lines, and this is 8. By a very easy counting argument, we can prove that if we have a set containing n elements, then its power set will contain 2 to the power n elements. Suppose A is a finite set containing n elements, then P A will contain 2 to the power n elements. and the notation that we have used here is quite general. So, if we have a finite set, then by writing that set symbol within two vertical lines, we denote the number of elements in that set. Suppose S is a finite set, then is the number of elements in S. In today's lecture, we have started with the definition, or not really the definition, but a description of the idea of a set. We have talked about how to conceive of a universe and then conceive of some collections of specific objects within the universe, and after that basic description we have defined the terms such as subsets, proper subsets, null sets, null set or empty set, and lastly we have talked about power sets, and number of elements in a set, In the next lectures, we will discuss more on sets such as operations on sets and laws of set operations, but this is all for today. Thank you.